I'd like to remember that all the students that are interested in doing lab next Tuesday, they must book their seat through the website, okay, to the student website. Okay. I put in a specific folder under Materiale section in the same website the guideline for the lab and all the datasheets that are required to performing correctly all the operation, all the points in the laboratory. Okay, so let's continue what we are talking about. That is, first of all, I'd like to say complete the discussion about the dead time. Okay, I remember that yesterday we left dead time discussion, dead time or say blanking time. Sometimes dead, band. Okay, several names for the same concept. Okay, you have to delay the rising edge, so the turn on of the switch, in order to have to insert a specific situation in which all the switches in the same leg are left open. Okay, so the current is conducted by the freewheeling diode. Delta V naught, so the difference between the V naught average value without this dead time minus the average value of the output with the dead time, okay, this is the correct definition, is exactly what I already wrote yesterday. Is 2 dsVd anytime the current I naught is positive and is negative 2 d delta dsVd when the current is negative. Okay, this comes directly from our previous results that we fully derived for the half bridge. Okay, in the full bridge, now we have, let's say, two legs in parallel, so we have two half bridge in parallel, so we can derive easily. Okay, this is the four quadrant converter. So if you want the same results can also be reported into a graph of the output voltage, average value, and the control voltage. The control voltage ranges from 0 to the peak value of the pulse width modulator carrier. And then we have, let's say, plus Vt, negative Vt. And this is the curve with T delta equal to 0. So when the current is positive, we have something like this. So we have a difference here between the ideal situation, not that time, and the situation which you have at that time, which is exactly this one, this positive one. Okay, and then you have the curve, which is slight shifted upward, which is the situation which the current is negative. Okay, so now the difference becomes negative. So that time is something that leads to an error in the average voltage. Feedback control can help to say avoid this difference by, say, selecting the correct duty cycle for this for recover this error. Okay, so this completes the discussion about the dead time as a derivation from the half-bridge discussion. Let me do some example in which I can compare the behavior of the four-quadrant converter, unipolar and bipolar pulse width modulator in terms of the maximum ripple of the current flowing to the load. Okay, so let's compute the maximum peak to peak current ripple IO, let's say I note peak to peak for unipolar pulse width modulator and the bipolar pulse width modulator. Okay, this is our simple exercise. Let's start with the bipolar pulse width modulator. Because this is a little bit simpler than the case of unipolar one. Remember that we already had this computation for the two-quadrant converter, okay? And then we can compare also these results with the two-quadrant converter ripple. For the bipolar pulse width modulator, we know that whatever is the average output voltage, V naught average, the instantaneous voltage has always this behavior. It's a rectangular waveform, bipolar rectangular waveform, for example, this one. Ranging from negative VT to plus VT. This time interval is exactly Ts, and this pulse is, by construction, remember our waveforms that we studied yesterday, is dA multiplied Ts. Okay. In this situation, I plotted the case for, say, V naught average value positive. Here. If you want to plot the same output voltage for the case in which V naught average value is negative, then I have just to make the positive pulses narrower, and then we can get negative. But the waveform is always bipolar in that it has the same shape. What about the current flowing through the load? So the current I naught, the current has a behavior which is, let's say, rising up during the positive pulse, negative, so descending behavior during the negative one. Okay, so this is the current I naught versus T. This is just the ripple computation. Of course, this current, this ripple is superimposed onto a pedestal, an offset, which is a, say, DC current. Okay, is an offset above the continuous value. Okay, this is just a ripple component, because in this case I'm interested just in this peak-to-peak ripple, which is exactly this quantity. Before, say, starting this computation, let me see if effectively the output voltage is given by, remember, 2 dA minus 1 VT. Okay. This is the waveform of the voltage at the output. So the average value is given by VD multiplied dA TS, and this is this area here, minus Vd 1 minus dIA ds, and this is this area here, and then we have to divide by ts. And it's easy to see that this quantity is exactly what, say, we found out as say general consideration about the 4-quadrant converter. Okay, so this is just say to verify what we already known from the previous situation. So we know the average value of the output voltage can be negative or positive depending on the value of the duty cycle DIA. We call DIA minus 1 the equivalent duty cycle, if I remember. So what is the slope here of this output current, which is rising up? In order to find out the AC component of this current, we have to consider which is the AC circuit. Okay, and the AC circuit is that we can obtain by replacing the 4-quadrant converter by a voltage, which is just the AC contribution of the output. We can use the inductance. Okay, let me skip for a moment the resistance, as we did for the example in the 2-quadrant converter. Remember, the impedance of the resistance, okay, is just less than that of the inductance. Is that, if you want, this is not correct because you have also this resistance, but just to simplify a little bit computation, then we have to consider no back EMF, because the back EMF is just a DC component. Okay, this is the AC equivalent circuit at the output. Okay, LA. So you can see the voltage across the inductance is exactly the AC component of the voltage V0. Okay, the C component, the voltage V0, can be obtained by taking all the voltage, instantaneous value, and subtract to it the average value. Okay, this is the AC component. So this slope is simply given by, let me put here, Vd minus V0 average value over L. Okay. What is the ripple? The ripple is that you have the slope. I know that the slope lasts for this interval, and this interval is TIA TS, and so we can get the ripple. The peak-to-peak ripple is Vd minus V0 L, this is called LA, multiply TIA TS. Okay, this quantity is exactly the peak-to-peak ripple. Let me just consider that V0 average value is the quantity that I derived before. It's here. So is 2 DIA minus 1 Vd LA, let me put the frequency instead of the period, TS, multiply DIA. So algebraic manipulation, we can collect Vd. Vd is 1 minus 2 DIA plus 1 multiply DIA LA Fs. So this is 2 Vd 1 minus DIA over LA Fs DIA. Okay, so now we have to search for the maximum ripple that we can get in this bipolar pulse width modulator. That means that I have to take the derivative of this ripple with respect to the duty cycle DIA and put this 0. Okay, in this way I can find the duty cycle DIA for which I get the maximum. and this is you get the multiplication here. You get dA minus dA square. So this is 2 PD 1 minus 2 dA LA Fs equal to 0. And so let me put here dA star, which is the duty cycle for which you get the maximum. This is 1F. Okay. In that situation, the peak-to-peak ripple maximum obtained for 1F. Simply put 1F in the previous expression of the peak-to-peak ripple, and this is 2VT1 minus 1F multiplied 1F again, LAFS. This is VD over 2 LAFS. So this is the maximum ripple that you can have for bipolar. Okay, we obtained this value for the output voltage, which is positive, the average value, but since nothing changes in the waveform, in the time domain waveform, the output voltage, even in the situation in which the average is negative, okay, we can get these results as a general conclusion for both positive or negative average value. Okay, this is for V naught, which is positive, and also for V naught negative. Remember which is the maximum ripple for the two-quadrant converter. For two-quadrant converters, the maximum I naught peak-to-peak is again obtained for a duty cycle, which is 1F, and this was VD over 4 LAFS. Okay, for two-quadrant converter. So in this case, the ripple that we can get for the bipolar pulse width modulator for quadrant is, let's say, twice the maximum ripple that you can get in the two-quadrant converter. We can also put this ripple on a plot, which we have the duty cycle ranging from 0 to 1. And this is the peak-to-peak ripple. Okay. So this means simply that you have to plot this function here. Okay. This function for the duty cycle, which is 0, is 0, and it is when duty cycle is 1 is also 0, and that is a maximum at 1F. So it's something like this. The maximum value is VT over 4, 2 LAFS. Okay, this for 4-quadrant bipolar pulse width modulation. And what happens for the two-quadrant converter? You have a similar behavior, but then the maximum value is VD over 4 LAFS. This is for two-quadrant converters. The horizontal axis, which is in a DAA scale, can we also transformed into the output voltage. Okay, V naught is simply 2 dia minus 1 multiplied Vd. So we can get that here you have 0, then you can have Vd, negative Vd here. Okay, this is for the 4-quadrant converter. Okay, 4-quadrant converter. So let me change now the modulation. So let's go to the unipolar pulse width modulation. Let's see what happened. Now we have to be aware about that the fact that if you want to get, say, output voltage, the average value positive, you get a total positive output voltage, instantaneous value. Okay, because this is a unipolar modulation. When you want to get a negative average value of the output voltage, you have a totally negative output voltage. So we have two different, say, waveforms for two different signs of the average output voltage. So let's start. So we have to consider both the cases. So let's start with the situation A, let's say output voltage average value, which is positive. In this situation, the output voltage is, let's say, unipolar and totally positive. Something like this. Okay. This interval here now is Ts, because the frequency of this waveform is twice the switching frequency. Okay, so this is Ts over Tu. Now the width of this pulse is, remember, by the construction we had previously, is dia minus dB multiplied Ts over 2. And this quantity, since dB is 1 minus dia, by definition, this is 2 dia minus 1 Ts over 2. Okay? This is the width of each pulse you have here. By the way, let's compute the average value. Okay? And remember that we know that you should have 2 dia minus 1 Vd, exactly as in the bipolar pulse width modulator case. By, say, looking at this waveform, I have to consider these two pulses here and to average the area over Ts. This area is Vd, which is the 8th, that multiplies the width, and the width is 2 dia minus 1 Ts over 2 over Ts, and this is multiplied by 2 because we have two pulses. Okay, so this 2 is cancel out, Ts is Ts, and then you get exactly what we already know to have. Okay, just as a verification. This is the output current, and the output current, let's see just the ripple component, so the alternated current component, is something like this. It's rising up here and is something that goes down here. The peak-to-peak value is exactly what we are searching for, the ripple. Okay. So what is the ripple component? Then you have to consider what is the AC component of the voltage, and the AC component of the voltage is the output voltage less the average value. This is just the AC component, and so the slope here is Vd minus the average value over La. If you want to get the ripple, then you have to multiply this slope by the duration of the interval, for example, in which the current goes up. And this interval is exactly 2 TA minus 1 TS over 2. So I not peak to peak is VD V naught over LA multiplied 2 TA minus 1 TS over 2. That, remember that we have this output voltage average value, so we can use this value here. I naught peak to peak is VD minus 2 times DA minus 1 over LA 2 times FS multiplying 2 times DA minus 1. Then we have also VD here. So some algebraic, very simple manipulation. 2 times VD. If you collect VD here, okay, you can get 1 minus 2 times the EA plus 1. So 2 minus 2 times the EA. I can also collect the 2, and then you have 1 minus the EA. Over 2 times LA FS 2 times DA minus 1. So here we have the 2 and the 2 are, they cancel out each other. Then if you multiply the two parentheses containing the duty cycle DA, you can get this final expression, okay? 3 times DA minus 2 times DA square minus 1 divided LAFS. Okay, this is the expression for the peak to peak. Now I want to compute the maximum ripple. So the maximum ripple is simply the time, the derivative versus the duty cycle of this quantity, and then I can get 0 in order to get the duty cycle for which you get the maximum ripple. And this is VD 3 minus 4 DIA star over LAFS. So we know that from this equation, the duty cycle for which you have the maximum ripple is 3 over 4. Okay. Put this duty cycle inside the ripple expression, then you can get that the ripple, the maximum value, which by the way is obtained for duty cycle 3 over 4, is VD over 8 LAFS. This is just for V naught average value, which is positive. And by the way, this value is the smallest one found out so far. Okay, this is exactly the consequence of the fact that you have an output voltage that is switching at twice the switching frequency. Okay, so in that situation, you, with the same filters at the output, so with the same motors, with the same LA and array, then you can get a more effective filtering action, that the modulator at the output is more effective in filtering out all high order harmonics. And this is something that you can see practically on the amount of the ripple of the current, okay, which is, let's say, the residual of the switching frequency is effectively reduced. What happens when the output voltage is negative? So let me put the case B. Output voltage average value is negative. Now the situation is that the output voltage is totally negative. Something like this. So we have 0 and negative Vt. The average value is here. Negative value. The width is again 2 times dIA minus 1 ds over 2, and this is ds. Okay. How can we get the current? The current is simply, this is V naught over T, the current I naught is can be obtained by taking into account just the AC component of the waveform, so the overall V naught as a function of T subtracted by the average value. And then you can get something which is, let me change color. Something like this one. This is the I naught, and the ripple is exactly what I'm searching for. So in order to find out the ripple, let me just discuss the slope. Slope here is, say, the voltage, the instantaneous voltage, to which you subtract the average value. So it is negative Vt minus V naught over L. So this is minus Vt plus 2 times dIA minus 1 Vt. This is negative 2 times dIA Vt over LA. As you can see now, this is the slope is negative, okay, when you have, say, negative voltage. What about the current? The peak-to-peak is simply given by the slope multiplied by the duration. The slope is, let me put now the absolute value, because I'm using the negative slope, so if I do not put absolute value, I can get the negative peak-to-peak value, which is a nonsense. So 2 times dIA Vd over LA multiplied the duration, which is 2 dA minus 1 ds over 2. The 2 and the 2 simplify each other, and then you have 2 times dIA square minus dIA Vd over LA Fs. Okay, this is the quantity you have to differentiate. With respect to the duty cycle, put it to 0 to find out which is the duty cycle for which you have the maximum. Okay, you get Vd over 4 dIA minus 1 LAFS 0. So you can have dIA 1/4. Put this duty cycle into the previous expression of the current ripple, and then you can see that you will get the same maximum ripple obtained before, Vd over 8 LAFS, but this is for V naught negative. Okay, so let me just graphically represent this this quantity. Here, I have something which is f, this value, here, and then something like this. It's for 1/4, and this is 3/4. Okay, this is obtained 1/4 when the voltage is negative, and 3/4 when the voltage is positive. So here you can see that the immediately that the effect of having a switching frequency is just to reduce the, say, residual ripple in the output current due to the switching action, as I said before. So basically, this is the major advantage of these modulation techniques versus the bipolar one. And see also what happens here. Okay, when you have the cycle 1F, the ripple is say null. And why this happen? Especially compared to the, for example, the 4-quadrant converter in a bipolar modulation, which is say the maximum ripple is obtained. Okay, so this is the another basic difference. This is simply to understand, very simple to understand, because if you look at the, say, the way unipolar modulation is working, you can see, for example, what happens. This is the triangular voltage in the modulator when you have the duty cycle 1F. For having the A1F, the control voltage is exactly half the value of the triangular one. So it is exactly here. Okay. This is the control voltage for the leg A. What about the control voltage for the leg B? Is the triangular peak minus the control voltage. So basically, this is also the control voltage for the leg B. This is the only case in which you have the same control voltages for the leg A and B in the unipolar pulse width modulator. So if you can, if you plot the, say, QA, for example, the QA is something like this. Etc. And QB is, now I'm, say, answering the question. Okay, let me just do to finish this plot. QB is obtained by using the same rules, and so you have the same QB, the same switching function as QA. So QB is basically the same as QA. So what happens to the output voltage? The output voltage is constant, and it is null. So we have no ripple because we have no voltage. The voltage is null, and so we have no currents. The current is basically is not working. It's not flowing. Just let me to answer the question. Simonetti is worried about the slides. This is not, I don't know, I don't remember, but I think this is not present in the slides. Okay. Check by yourself, but I don't remember well. So bipolar pulse width modulator. What happens when the duty cycle is 1F? For having duty cycle 1F, the control voltage is exactly here. Okay, V control is V triangular peak divided by 2, and so I can have the same QA as before. Having duty cycle of 50%, because now the control voltage is exactly half value of the peak, the triangular value. What happens to the QB? QB is, let's say, the control voltage for the leg B is the same control voltage for the leg A, but now the generation low is the opposite one. So I have a square waveform, again, duty cycle 50%, but the phase, if you want, is shifted. Okay, is 180 degrees shifted in phase. So what happens to the output voltage? The output voltage now is something like this. Is a square waveform, so having duty cycle of 50%, or this is not correct because I have to put exactly. I think that you understand the concept. Okay, is negative VT plus VT, and the duty cycle of this waveform is exactly 50%. So it means that you have this part here, which has the same value of the negative part. So the average value, okay, is null, as it happens before. But in a unipolar pulse width modulator, an average value which is null is obtained by considering a null, say, waveform of the voltage VT. Here, the average value is null because I have a bipolar waveform having duty cycle of 50%. This leads to have the maximum ripple, okay? While here the ripple is totally, there is no, the current is null flowing to the output, so there is no ripple. Okay. Have you any questions about this simple computation, in my view? Something which is not clear? Let me continue by doing some, say, consideration about this 4-quadrant converter, okay? Let me put here the complete graph using IGBT of this 4-quadrant converter. Is something that I so TA plus TA minus for the leg A, then you have the leg B, so this is TB plus DB minus DA plus DA minus DB minus DB plus. Then here we have the source. We always have a capacitor, the input voltage. This node is called A, and this is the node B. So the load is connected here. Let me put here a generic load, and then it's connected here between the node A and the node B. So I described before this 4-quadrant converter by saying that if you put I naught average value and V naught average value, this specific circuit is a 4-quadrant converter. So it it will be employed for generating bidirectional current, so the current can be positive or negative, and also reversible voltage. The voltage VO is the voltage between the node A and B. Okay, so I can have operation point in all these 4 quadrant converters. Previously, I described the 2 quadrant converter. Okay, and the 2 quadrant converter is just one leg. Okay, it's a half bridge, and this half bridge can be employed to get bidirectionality of the output current, but the output voltage is just positive. Okay, so in the 2 quadrant converter, I'm working specifically in this area here. Okay, so the blue area is for the 2 quadrant converters, and the yellow one is for the 4 quadrant converter. Now my question is, what about if I want to build a converter, a DC-DC converter, for example, that can be employed for generating a reversible voltage, so voltage that can be positive or negative, but just unidirectional current. So my goal is to obtain something that is working in these other 2 quadrants. Okay, so I have another 2 quadrants converter. This is a 2 quadrant converter in which I have output voltage reversible and only positive current. Okay, while here is another 2 quadrant converter, but in this 2 quadrant converter I have just, say, not reversible voltage, and I have bidirectional current. Okay, so are 2 different 2 quadrant converters. Okay, they are, let's say, in their operation, they are, say, different. Okay, so what I can use this 4 quadrant converter here, just say modifying something in order to get this 2 quadrant converter. Okay, since I want to get only positive current, okay, I want to get only positive current, I can eliminate all that devices that in their operation are not able to conduct a current which is positive. Okay, so let's see what happens. Okay, I need a current which is positive. A current is always directed in, let's say, towards right in this drawing. Okay, from the node A towards the node B. So I have 4 transistors and 4 diodes. Okay, not all these devices support a current flowing in that specific direction, and then I must skip them. I can, say, eliminate them from the circuit. Okay, so for example, let's put these. Let's start with the transistor TA plus. The transistor TA plus can only have a current flowing from the collector to the emitter, so in this direction. And as you can see, this direction is concordant to the current at the output. So this is something, the transistor TA plus, that I have to maintain in the final circuits in order to, say, support this current flowing. What happens to the DA plus? DA plus is a diode that can conduct a current from, let's say, the anode to the cathode. But when this happens, the current is no more having this direction. Only a current which is negative can be conducted towards the diode DA plus. A current flow in this direction here, okay, can work, can, say, be supported from this diode here. So it is a current which is negative. But this is not the case. I'm searching for a, say, converter that is able to support just a positive current. So that means that I can skip this component here. I can't put this component off because it's never being used in this circuit. Okay, so it is totally useless. What happens to the transistor TA minus? Okay, TA minus again is a device that conducts current in that direction, but this direction is something that can be only supported when the current I naught flow in the opposite direction with respect to the positive one. So again, this transistor is useless in my, say, only positive output current circuit. So it's something that I can eliminate. What about dB plus? dB plus, sorry, what about dA minus? dA minus is a diode that supports a current flowing in this way, and so this current is exactly the current that, say, is concordant to the output current, positive current. So this is something that I have to maintain in my final circuit. What happens to dB plus? dB plus is a current flowing here, so it's a current entering node B. If this is entering node B, it means that has this behavior, this direction, which is opposite to the positive current. So it's something that I can, say, eliminate. I can delete from this circuit. dB plus, say, is conducting a current from the anode to the cathode, and this current is concordant to the presence of a positive current. Okay, is the current flowing here. So this can be maintained in my final circuit. What about TB minus? TB minus is a current flowing here, so it means that you have a current flowing here in this way, and this is a positive current. So this is okay. I have to consider it in my circuit. What about dB minus? dB minus is a diode for, say, a current flow in this direction, but this direction is a current that, say, goes opposite to I naught. So I can delete from the circuit. Okay, so basically, in order to support only a positive current, dA plus, dA minus, TB plus, and dB minus are not useful for conducting a positive current. Okay. So this means that from the 4-quadrant converter, simply eliminating some devices, I can have oh, this is not something that I have to use later, that I put there just to remind me. The problem now is that I have to copy this one. Let me just a few seconds. Okay. 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 So let me just redraw my circuits modified as I told you. So now instead of having 8 devices, I have just 4 devices, 2 transistors and 2 diodes. So this is dA minus, dA plus, This is the node A. This is the B plus, T B minus. This is the node B. And so here I have the load, okay, the generic load I considered before. This is the circuits in which I have the current flow in this direction, okay? And this is the voltage V0. So the current here can only be positive, okay? There is no way to have a current which is, say, negative, because there is no device that can support this negative current. The current can only be positive. What about the voltage? The voltage across the load depends on the status of the switch. For example, if TA plus and TB minus are both on, okay, then the voltage V0 is the same of the voltage VD. Okay, what about if the TA plus and TB minus are both off? But in that situation, the current can only flow through the diode TA minus and dB plus. Okay, and so this means that my voltage V0 over T is negative VD. So as you can see, I can get, say, bidirectional voltage. The current is only, say, flowing only in one direction, the positive one. The voltage can be, say, bidirectional. What about if, I don't know, TA plus is off and TB minus is on? In that situation, the current flow in this mesh of the circuit, okay? And so the voltage at the output basically is, let's say, negative, equal to the value of the voltage, the forward voltage across the diode. But basically, this is almost null. Okay, we can say it should be negative VF if you want. What happens if TA plus is on and TB minus is off? Now the current flow in this, say, mesh here, high side transistor and diode, but the same output voltage here is V0 is, say, almost zero. Basically, it's negative VF. Okay, so this is a bidirectional, is a two-quadrant converters having a current which is only positive, so I get just one quadrant for the volt for the current, but just I have the bidirectionality in the voltage. Now here I put a generic load, okay? But what about if in place of that generic load I put the equivalent circuit of a phase, for example, of a stepper motor? Replace the generic load with a phase of a stepper motor. Okay, here. So let me redraw again the circuits. I have TA plus, and this is the node A, and the node A is connected to the diode GA minus. Here we have the generic phase of a stepper motor, remember, RA, RA. Then I have the diode DB plus, and here we have the transistor TB minus. Then we have the capacitor and the voltage VD. Remember the circuit? We already seen this circuit. Okay, we call this circuit asymmetrical. We call the circuit, sorry, chopper. Chopper circuit for unipolar steppers. Okay, this is the node B. This is not exactly the shape I use for the stepper motor when we talked about this circuit. Okay, but it's simply to understand that if I put transistor TA plus here, then we have the node A. From the node A, I put my phase, and then I have the node B. So I'm going in this direction here by description. I have the node B. From the node B, I have the transistor, which is TB minus. Okay. And then from the emitter here, I have the cathode, sorry, the anode of DA minus here. And from the collector of this transistor, you have the cathode of DB plus, and the anode is connected to the node B. And then I have here the supply. Now, this the circuit which is redrawn in this way maybe sounds to be more familiar to you, because this is exactly the chopper circuit that I previously discussed for, say, stepper motor. Okay, stepper motor, unipolar stepper motor only requires a current flowing in this direction. Okay, but remember that this circuit has the ability to generate a reversible voltage, which is what I really need for, say, having a faster turn on and turn off action. Okay, so this is what I require. So I require a two-quadrant converter having, say, not bidirectionality of the current, but reversibility of the voltage. Okay, we derive the same circuit, the same topology, starting from the four-quadrant converter, which is the most general circuit that can be employed for the DC operation. Okay, so this is what we can have the same circuit here. Sometimes this circuit, this one, which is the two-quadrant reversible voltage and unipolar current, is also called asymmetrical full bridge. Asymmetrical because the two legs are not exactly the same. Okay, in terms of architecture. Okay, you have TA plus and DA minus, and the other side you have the opposite, DB plus, DB minus. Okay, the asymmetrical full bridge is what we called the chopper circuit, chopper driver for unipolar stepper previously discussed. Just remain on this topic. Okay, the topic is regarding the stepper motor. Remember that I said when we talked about the stepper motor that now we develop some insight for driver or unipolar stepper motor, because we don't have all the information we need for discussing at that time, the bipolar stepper motor. Okay, bipolar stepper motor are those specific steppers that can be operated by reversing the direction of the current that flow through the different phases. Okay, remember previous discussion of the stepper motor. But now we have this possibility. Okay, and because you know that there exists the four-quadrant converter in which you can have the bidirectionality of the current. Okay, so here, if you want to do the driver, let me say drivers for bipolar steppers, I can simply use the 4-quadrant converter. I'm using a IGBTs, but you can also use MOSFET, of course. My load now is one single phase of our stepper motor. Okay, as you can see, by using this 4-quadrant converter, I can have a current flowing here that can be positive, but so flowing in this direction, but can be also negative, depending on, say, the duty cycle, DIA and dB of the two legs. And this can be, say, employed for driving a current in both directions in the phases of these steppers. And this can be used for, and this is exactly the driver that you can find in integrated circuits for stepper motors. Okay, so this is just, if you want, an extension of our previous discussion about the driver for steppers. Okay, so 4-quadrant converter as a driver for bipolar stepper motors. Have you questions regarding this say, topic or the previous explanations, whatever you think is not clear? Everything is okay. So I think that we can have a little break here because I'm going to change the topic. Okay. After the break, I'll start an exercise, a design exercise of a circuit like the circuit I explained up to now for DC-DC 2-quadrant converter. Okay. And before starting computation and getting involved in the, say, designing, I need a little, let's say, introduce to this exercise. So I get some, say, theory about the actuators I'd like to drive with my stepper. Sorry, with my DC-DC bidirectional converter. Okay, so I prefer to start after the break, then start here and then break. Okay. So let's have, let's say 10 minutes break. So 1 p.m. we can start again the lecture, okay? So I'd like to start now a design exercise, and I want to be, in order to make this design more interesting, I want to, say, cast the computations for a specific actuator. Okay, so let me just to introduce you the specific application and the specific kind of actuators I want to drive. Okay, so this topic is under the generic title of piezoelectric actuator. Sometimes they are called piezo actuators. Okay, so let's start a short introduction. In nature, exists say a specific effect which is called the direct piezoelectric effect, by which if a force is applied to the crystal, say a quartz crystal, for example, let me just exemplify the discussion by having this crystal. Okay, for example, in this way, let me put here a force which is, say, act on this vertical direction, for example. The force is acting here. Then a specific electric field is developed across its terminal. Okay, for example, if you have some, say, plates here at the bottom, and then you are able to measure the electric field, so for example the voltage, then you can see that there is a voltage which is developed as a direct consequence of the mechanical stress induced on this specific kind of materials. Okay, this is the direct piezoelectric effect, but the inverse is also true. So this is the, let's say, inverse piezoelectric effect. And by inverse piezoelectric effect, it means that if a voltage was applied across the same crystal, for example, then the electric field that is generated by the application of this voltage cause the crystal to be deformed. So let me exemplify by having the same quartz. Then suppose that I have two, say, plates here. Then I have a voltage. This voltage applied here induces a specific electric field on these materials. And then it happens that I have a deformation. For example, the same quartz can be, say, elongated in one direction. Okay, there is, if this is L0, the length of this material for no voltage applied, then you can have a deformation, okay, that is induced by the electric field. So this is what is basically the piezoelectric effect. This type of behavior is present, say, naturally in some crystal, so they exhibit these phenomena. And so, for example, typical, there are several different materials. Just a few of them are the barium titanate. It is BaTiO3, or the lead zirconate, or also the lead titanate zirconate, that are the most diffused, also called P-zeta-T material. Okay, they are ceramic materials that can be employed in say, this kind of applications, and sometimes the piezoelectric effect that comes naturally must be enhanced in some way. And so in order to enhance this effect, the materials are subjected to a specific let's say, process that is called the Pauling treatment. Okay, so there is a process which is called Pauling treatment. Basically, it means that you have to expose this material to a very strong electric field at a temperature which is below what is called the Curie point. The Curie point is the temperature at which the material loses the piezoelectric properties. Okay, then, for example, if you apply a specific high voltage, let's say that has this behavior. This is just an example. Okay, this way, this is the voltage V that is applied for a certain time interval with a specific temperature below the Curie point. Then we can enhance this behavior. Okay, so we can have more effective piezo actuators, more effective piezo materials. Typically, the voltage which is applied for this pooling treatment is just a unipolar voltage. Means that you have to apply, for example, just a positive voltage like in this figure. Because if you apply the same materials a negative voltage, then the negative voltage can have what is called a depooling effect. So it acts in order to reduce the piezoelectric activity. Okay, so it basically this pooling treatment performed by applying only positive voltage. Okay, because negative voltage can have an adverse effect, but we have to say that sometimes this is not true. But for the rest of my discussion, suppose that this kind of devices can only accept positive voltage for, say, enhance their properties and for getting the piezoelectric effect. Okay, because the voltage which is negative can act as a depooling, so reducing the piezoelectric effect. But anyway, this is the mainly characteristics. I have to say that, for example, when you have this voltage here applied to the material, of course, you have a deformation of the piezo materials that that comes in all the direction. Okay, so you can have a, say, deformation in this length, for example. So as you can see, the same direction of the applied electric field. And then you have also something that happens in the, say, opposite direction. Okay, for example, that can be narrow in a direction that are orthogonal to the direction of the electric field. Basically, the piezoelectric effect is very large in the direction that is in parallel to the direction of the applied electric field. Okay, so as you can see here, this effect of deformation, which is exactly in parallel to the applied electric field, is much better, much higher with respect to this other. Okay, so this is often, say, is exploited. Typically, the direction are indicated in this way in the crystallography, that are 3, say, the direction which is the vertical. Then we have the 1 and 2 that are the, or say, the direction in the plane. Yes, is 2. Okay. So, for example, if I apply an electric field in the direction which is 3, you have, say, a strong deformation, elongation in the direction which is also 3. And then you have a less elongation, deformation in direction 1 and 2. So let me consider the elongation that you can have when you when you apply a voltage or electric field into a piezoelectric crystal as delta LP. Okay, this is the deformation induced in the material on P zeta T, so the crystal, the piezoelectric crystal. It can be shown that this deformation is given by the product of a, say, quantity, which is called the piezoelectric displacement constant multiplied the L0, which is the size, the dimension of the crystal without any external voltage or electric field excitation. Okay, so the rest length of the material. This piezoelectric displacement constant is the ratio between the elongation and the rest position, rest dimension. So is something which is, let's say, dimensionless. And then if there is also the, say, possibility to better characterize this constant as the product of a specific coefficient, which is called the piezoelectric coefficient, multiplied the electric field which is applied. Okay, so there is this direct relationship. This is a first order approximation of a phenomenon which can be, let's say, a little bit complicated to be described, but let's say for our purpose this is enough. What about the terms, the subscript 3,3 means that the first index is the direction of the electric field applied to the crystal. So this is the direction of E, while 3, the second subscript, is the direction of the, say, displacement, of the elongation. In this case, D33 means that I am applying, as I showed you before, this electric field by means of this voltage along, say, the vertical direction, and I get the maximum elongation in the same direction. Of course, this equation here neglect all other contribution, for example, D31, etc., 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 that can be skipped in our first direction. Okay, so if I put this expression, this one, into the this quantity here, I can get that delta LP, the obtained deformation, is D3 free multiplied E multiplied L0. Now here we get the multiplication of an electric field multiplied the length, and this is exactly the definition of a voltage. So you can get that this is D33 multiplied the voltage. Okay, so you can get a direct relationship between the voltage that you apply to the crystal and the deformation you can get. Typically, this can be also plotted in a graph like here, like this, for example, delta LP versus B, which is something like this. So the slope here is exactly D33, but this is also a, say, ideal situation. Typically, when you get, let's say, increasing the voltage as an elongation is not the same that you can get when you're reducing the voltage. So you have a sort of hysteresis, something which is better described by, say, something like this. Okay, so something that is obtained in this way when you are increasing the voltage and when you're decreasing something like this. Okay, so anyway, we can see that this is a relationship that we can have. What about the electric field that you are applying here? Okay, because of course the electric field cannot be chosen to be whatever electric field you have in mind. Typically, because if you are exceeding a specific critical threshold of this electric field, the material experiences some, let's say, mechanical stresses that can lead to the destruction of the component. You cannot exploit no more the piezoelectric effect. So you have a maximum electric field, and this maximum electric field is in the range of 1 to 2 kilovolt millimeters. Okay, so you are allowed to apply an electric field to these piezo materials up to this value. And what about the elongation? Is this elongation, say, directly applicable? So it is large enough to use this piezo actuator as piezo material as an actuator? Typically, the delta LP is not so large. We can say that this piezoelectric displacement coefficient here, which is exactly the ratio between the two, is about, say, 0.1%. Okay, so it means that you have a 100 millimeter length L0, then your delta LP is 0.1 millimeter. Okay, so it is very short. It's not too much. Let's consider, for example, a simple, let's say, example, not to understand what is the problem. The problem, let's suppose that I have an, say, slice of piezo materials which has a rest length of 1 millimeter. supposing that my maximum elongation delta LP is exactly 0.1% of L0. So I get that my constant is exactly 0.1%. This means that this is 1 micrometer. What is the maximum voltage that you can apply here? The maximum voltage is the maximum electric field multiplied L0. The maximum electric field, suppose that I have 1 kilovolt millimeters, and then I have exactly 1 millimeters. So I have to apply 1 kilovolt, okay, in order to get 1 micrometer of elongation. So as you can see here, a single portion of length L0 of piezo material, P zeta T, is not directly say useful, okay, because you have to apply a very large voltage to it in order to have, say, a very small elongation, which is, say, something which is not useful. This is the reason why typically all the piezo materials, in order to be employed as useful actuators, are organized in piezoelectric stacks. The piezoelectric stacks basically are construction by which you can connect more than one piece of PZT materials, okay? For example, suppose that I have these slice of material. Suppose that it is exactly my materials that I previously indicated. So it is 1 millimeter. Sorry. Suppose more general discussion. This is L0, whatever it is. I have the two metallic contact on the surface of this material. Okay, so I have to apply here the plus, and here I have the, sorry, let me put in red the plus terminal, and in black the negative one. Okay, so here I have another one, the same length, and suppose that now I have the negative here and the positive here, and so on. Positive here, negative here, etc., 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 up to the last one. So I have n of these elements, n p zeta t. Then suppose that I can connect this terminal here, so they connected here, they are connected here, etc., etc. So they are there is a galvanic connection between the terminals. So I have the plus and the minus. So we have here the batteries. And also I have all these terminals that are connected to, say, plus side, and these are connected to the minus side. So, for example, I have something like this. So basically, all the plus terminal are connected together, and also the minus terminal. And then I have here the battery. So what happens to this to this construction? Basically, I have that the total length now they are all the same, so it is n time the length L0. Just for, say, putting some numbers, supposing that I have n, which is 500, and suppose that L0 is 20 micrometer. Okay, typically this the length can be in the range of tens of micrometer up to, say, 1 millimeter. Okay, so this is something which is possible. So L total is 520 meters, so it is 1 millimeter. So the total length here is the same length that I have in the previous example, in which you have just one PZT materials. Okay, but now, which is the voltage that I have to apply? But the voltage that I apply is V maximum is E maximum multiply the length L0, which is, supposing 1 kilovolt millimeters multiplied 20 micron. And this is 20 volt. So if I put here 20 volt, I get on this quantity here, I can have, let's say, this is the maximum voltage that I can apply. And what is about the delta L that I can, delta LP that I can get from this quantity here? Delta LP is again n times the total delta LP of single elements. Okay, so it is 500 multiply, let's say, 0.1%, so 0.1 20 micron divides 100, and this is again 1 micron. So basically, in this example, I can get the same elongation, the overall elongation that I can have using just one single piece of piezoelectric materials, but the advantage that I can use a very lower voltage with respect to before. Okay, 1 kilovolt versus 20 volt. 1 micrometer is not, let's say, something that can be exploited, but the discussion is already, say, is in this. I can increase this voltage here, maybe having L0 maybe a little bit larger, that I can increase the elongation without, say, having 1 kilovolt. Okay, so if I have the same overall stack dimension, I can get the same elongation with lower voltage. Or if I get the same voltage, I can get very large elongation with the same dimension of the stack. So this is typically the application that you can find for this kind of piezo materials. Okay. Let me just to discuss a little bit the fact that what is the because we are interested in understanding which can be the electronic drivers for this kind of piezo actuator. Okay, so it will be helpful to understand which is the electrical model of this piezo actuator. Okay, it's a materials that when you apply a voltage as an elongation, but say in terms of, let's say, electrical model, how can describe this material? So typically what happens is that if you look at the electrical model of these materials, that you can see something like that. A capacitor here, and then several, let's say, theoretically infinite branches like this. C1, R1, L1, and then you have another one here, L2, C2, R2, all these branches that are C, R, and L, let me put N here, have a behavior that is like that of a series resonator. So if you look at the impedance of this circuit, basically from the input terminals, if you look at the impedance versus the frequency, you can see something like this. Etc. Several, say, resonance and anti-resonance behavior. These are, say, due to specific frequency resonance, FR1, etc., that are depending on the branches that you have in series. So the model is very complicated, but anyway, if you are, and this is that's a typical application for, say, actuator. Of course, the piezoelectric material can find, say, a very wide range of application, but in order to use them as, say, mechanical actuators, if you drive that piezo materials with a source, and you are, say, using this material with a, say, driving frequency which is less than the first resonance here, F, say, 0 here, then the behavior is simply that of a single capacitor. So you are just using this first capacitance here as a basic model, but this is just done if you are driving your piezo material with a frequency which is less than the first resonance. Okay, so using P zeta T materials at frequencies lower than F0 leads to model the piezo material as a single capacitance. And this is my model. Okay, maybe it's a little bit simplified, but for our purposes is all we can is required for understanding the operation. Okay, so piezo material can be applied for several different situations. In say, specifically, they can say, be employed as actuators that are very, very, very fast and can produce motion in very precise, controlled manner. Okay, typically even sub nanometers increments. For example, they are typically applied in inkjet printers when inkjet printers were, say, common here, but also in several other different applications like, say, medical electronics, anti-vibration controllers, or also in the piezo injector in automotive systems. Okay? So they can be employed for very fast, very accurate motion, sub-nanometer application. So I introduced this behavior, so the piezo actuator, for this kind of very precise and fast movement. They act as a single capacitance. If we look at them for frequency under the first resonance of the behavior. So what does it mean? That I have a single capacitance. This is the model for my, say, piezo actuators. It means that the current flowing through it is a function of the time derivative of the voltage across it. Okay, this is what is what happens typically. So suppose that I want to consider a typical waveform of application. Remember what I said at the beginning. The voltage across these piezo actuators is better to be, say, unipolar. Okay, better to have just, for example, positive voltage and not simultaneously positive and negative voltage, because if you apply negative voltage, especially if their voltage are very large, these negative voltage applied to the materials can act as a dipoling source, so it reduces the piezo effect. Okay, so V should be, let's say, not reversible. Due to possible pooling effects. What about the current? The voltage is positive, but the voltage can have a variation. Okay, and the variation can be positive or can be negative. When you can have a variation which is positive, okay, the variation can be positive when I want to obtain a elongation, a deformation of my P zeta t. In that situation, I'm increasing the voltage up to, say, possible value, which is lower the maximum Vmax value I show you before, depending on the maximum electric field, in order to get the maximum elongation I can get. Then when I want to decrease and to, let's say, come back again to the rest position, then I have to decrease this voltage. Okay, so you can have the V over the T that can be positive or negative. Can be positive, say, for elongation, or negative for the rest position, for returning to the rest position. So what does it mean? That the current I flowing through this capacitor can be positive or it can be negative. So basically we need not reversible voltage applied to it, but bidirectional current. Okay, so this is what we are searching for this as a driver for this kind of circuit. Typically, this kind of requirement are most of the time obtained by using linear driver. Linear driver means power operational amplifier, okay, that are arranged in the way that is, say, they are work for driving this kind of circuit. Okay, so this is what is most of the time done. Of course, when you use drivers that are linear, so they are operated in their linear operating region, it means that you have higher dissipation. Okay, this is always the situation that you have to consider in linear application. What I'm trying to explain to you here is that driver is better when they are in switching mode operation. So when you are using reactive elements and switches in order to reduce the dissipated power and to increase the efficiency of the system. So what I'm searching here is not to develop something which is, say, linear. You can find integrated circuits that includes linear power operation amplifier for driving piezo actuators. But now I want to describe something which is in the switch mode operating mode. Okay, my power processing unit for this piezo actuator should be switch mode operating. But we already know a specific circuit which can be employed for driving this kind of capacitive load, which give us a not reversible voltage and a bidirectional current. This circuit is the two-quadrant converter, the half bridge. Okay, so let me put here a half bridge with MOSFET, for example. TA plus, TA minus, dA plus, dA minus, LA, or say, let's say L. Okay, this is the current port, and you have the voltage port, etc. You know that the current flowing here is a current that can be, say, made to be bidirectional, while the voltage that you have here is a voltage which is only positive. Okay, so I can use directly this circuit to drive my P zeta t, which is modeled by these capacitors. Okay, so this is exactly what I'm searching for, these circuits. Okay. Let me just copy this page. Okay, let me copy these ones. Okay, so suppose that now I have this to get a little bit, to acquire more insight into the behavior of this circuit. Let me consider what is the voltage V. The waveform of the voltage I'd like to apply across the piezoelectric material. Okay, suppose that my voltage is something like this. As you can see, this voltage has a maximum value. Okay, suppose that this voltage is the voltage by which I can get the elongation I need. Okay, so here there is a first phase. Let me call this, I don't know, A, in which you are linearly increasing the voltage. Why I need this slope here? Because here the voltage is dV over dt must be limited. Okay, so the action of applying a positive voltage should be somewhat limited in order to avoid the presence of some, let's say, mechanical failures inside the materials. Because the materials should be, say, break down, so it's no more, let's say, useful. Okay, so it means that when you want to get elongation, the acceleration of this movement should be limited. Okay, so I need this kind of slope. In this specific case, I'm, say, getting from a rest position, which is this one, L0, to a increasing elongation. In the situation that I have in between here, the voltage is, say, constant. So here I get the maximum elongation that I need. So here I have L0 plus delta LP here for my P zeta t. And then we start the phase, let's be called B, in which I have to, say, reduce again the dimension. So I want to get back to the rest L0 position. Okay, so from this position, I will have to get down. Again, this, say, phase should have a deceleration which is be controlled, so that the V on the T here is also limited. Okay, so let me call A, B, and this is the phase C. So A is the activation phase, okay, the energization phase. B is the de-energization phase, and C is the constant phase. Okay, this is the voltage V applied to a capacitor. So what about the voltage? Sorry, what about the current flowing to the piezo actuator? So let me put here a graph of the current. The current is, let's say, related to the capacitance and the voltage by this relationship, because we are in presence of a capacitance. Okay, so when you have a acceleration phase and energization phase, then you have a positive current. When you have voltage which is applied, it's constant, then you have no current at all. When you have here the phase in which the V on the T is negative, because you are, say, reducing the length of your material, then your current should be negative, okay? So you have bidirectional current and positive voltage, for example, unipolar voltage, to avoid the pooling effect. Where I have to say that in practical situation, even these very steep current that you can have here, or here, or here, or here, are something that you have to avoid. Also here, typically you have the I on the T, which must be limited, okay? This is simply due to the fact that if the I on the T is very large, this means that the I on the T is very large. So the voltage across this inductance should be very increasingly large. So it is not, sometimes it's not acceptable. So you have to, say, have this current to be controlled. But anyway, this is the ideal situation that I can have. Since this is the voltage and the current that I have to apply to my my piezoelectric actuator, these kind of electrical quantities are basically the voltage and the current, that the voltage is here and the current is here. They have the nature of average quantities that you can get at the output of my bidirectional converter. Okay, so these are average quantities. Okay, this is the voltage V is the average of the output of VAN, remember, and this is the average of the current. So in which way I can get this average voltage? Okay, the average voltage here is this behavior now. Okay, is something that changes with times. Remember that the average voltage of VAN in a two-quadrant converter is simply the product of the duty cycle of the unit switching function that I'm using for driving the two transistor in the half bridge, multiply the voltage VD. So it seems that it's like having a duty cycle that has a variation with time. Something that is, say, something like this. In the phase A, the duty cycle from 0 has to reach a value, let me call duty cycle maximum. And this is VAN divided VD. Okay, and VAN average value maximum is exactly Vmax. So this is, let's say, this duty cycle is also Vmax over Vd. From 0 to Vmax over Vd, then the duty cycle remains constant, and then the duty cycle is decreased from the maximum value down to, again, 0 here, okay, in the phase B. It is the variation of the duty cycle in order to get an average voltage that has this behavior here. Okay. Let me just see a little bit in details what does it mean using this kind of two-quadrant converter for driving this circuit. Okay, because the standard, we have to consider the standard way to modulate the switches in the half bridge, and something that we can change in order to have less power dissipation. Okay, so let me just discuss this point here. Maybe I need another page. Okay. Let me put, say, ideal switches in place of the MOSFET, okay, just to accelerate my drawing. This is the capacitive model of my piezo materials. Then I have TA plus, Ta minus, etc. In the first phase, what I call A, the energization phase, I provide energy to the capacitor. So I can provide charge to the capacitor for making it, let's say, longer. The duty cycle is increasing. Okay, duty cycle increasing means that from 0 to Vmax over Vd. The current is positive, so the current goes in this direction, the current I. Okay, so what happens? That in that situation, the current is provided by what? The current is not flowing to the diode because it's positive. So the current flows to this transistor here. When this transistor is closed. And when the transistor is open, the current flows to the diode here. So when Ta plus on, it conducts the current. When Ta plus is off, Da minus conducts the current I. This is Da minus and this is Ta plus. So the two devices that in this phase are, say, supporting, conducting the current high flowing to the load are Ta plus and Da minus. So this is a typical, remember, buck operation that we already know. Okay, we are providing power exactly here. So we are providing energy. The power here is positive. Okay. Basically, I am, say, operating this switch here. And remember that the unity switching function is something that is commanding the transistor Ta plus. Then I have Qa naught, which is commanding this transistor. So when this transistor Ta plus is on, Ta minus is off. When Ta plus is off, Ta minus is on. Okay, so transistor Ta minus switch in a complementary way with respect to Ta plus, and with a duty cycle which is increasing. Okay, so slowly from a, say, situation which you have duty cycle which is null, you have two unitary switching functions, Qa and Qa naught, which is 1 minus Qa. This is for the transistor Ta plus, and this is for the transistor Ta minus. So what happens? That let me just say exaggerate a little bit the phase that I call A, the energization phase. I have that here the duty cycle is, say, from 0 is increasing a little bit. Here I'm exaggerating, okay, but the duty cycle is increasing. What about the switch B? Is totally, say, complementary way, so it is symmetrical. Something like this, okay, is 1 minus Qa. So when the unity switching function is I, for example here, Ta plus is on, and when this is Ta minus, which is on. Okay, so this happens in this situation, buck operating mode. But first of all, look at what happens here. Even Ta minus becomes on, for example, here, here, and here. In that specific situation, the current is not conducted by Ta minus. In that situation, the current through Ta minus never conducts the current. So an alternative approach is to avoid, let's say, the switch on and off of the transistor Ta minus, because even if you have, let's say, that transistor Ta minus does not conduct the current, it dissipates power because it becomes on and off. So you have what is called the dynamic dissipation, the switching dissipation of the MOSFET. So another situation that can be employed, another alternative approach, is that you have that in that phase, the transistor Qa minus is always commanded to be off, for example. In that situation, you are avoiding to open and close Ta minus. The current is always conducted by the transistor Da minus in that situation when Ta plus is off. So the same situation, nothing changes, okay? But we are avoiding a contribution of the dynamic current, for example. What happens during the phase which I call B? During the phase that I call B, this is the energization phase. Basically, we are reducing the duty cycle, okay? We are reducing the duty cycle from the maximum value to 0, so the situation which is opposite to the previous one. What about the current? But again, let me just to draw the half bridge. Cl Ta plus Ta minus. Here the duty cycle reduces from V maximum over Vt down to 0, and the current is negative. So the current now enters. So what happens that when the current enters, the current cannot be conducted by the transistor Ta plus. It only can go to the diode Da plus, for example. Okay. This happens typically when you have IGBTs. Okay, when you have a MOSFET, the current can be also conducted by the MOSFET. Okay, by the way, so it depends on also on this on the devices you are using. When the transistor Ta minus is on, that the transistor can conduct the current. So basically, you can say that the current can be conducted by the diode and the transistor. Here we have what is called the typical boost operating mode. And in effect, in this situation, we are extracting power, say, from the piezo actuators, okay, in order to reduce the energy which is provided before. In that situation, leads to reduce the dimension of these piezo materials. Here, the same situation happens as before. If you want, in the phase, let's say, let me call here the phase B, Qa and Qa naught are something that can be something like this, a very large cycle. Then the cycle is reduced up to the point at which is almost null. Okay. What happens to the Qa naught? This is the complementary. Etc. etc. Even here, you can say that since the transistor, which is not conduct the current, especially if it is an IGBT, for example, then I can also consider to maintain always off this transistor. An alternative approach is to be considered this transistor always 0. So the Qa is always 0. Okay. Of course, this kind of reasoning will be dictated by power consideration and dissipation. Okay? You have to consider which is best solution for your overall power dissipation. If you take the transistor to be on and off, or maybe to consider just the diode to conduct the current. what happens during the phase which is called the phase C. The phase C here is the holding phase, so the phase in which you are maintaining the same elongation for a certain interval of time. Okay, here basically the voltage is the average voltage is constant, so the duty cycle is constant, and this is constant to Vmax over Vd, and the average current is null. Okay, this is the average current, which is null. What about the instantaneous current flowing in this circuit? Let me just redraw again. The half bridge. CL, etc. PD. The duty cycle is constant, meaning that you have a switching function commanding, say, the operation in a complementary way of these two switches, TA plus and TA minus. Okay. For example, you have this situation. The voltage V is a voltage which is constant. Okay. So here we are in the middle phase. The duty cycle is constant, for example, is, I don't know, something like this. The same width, okay? There is no difference. My drawing is not perfect. So what does it mean? That I'm switching on and off TA plus. So for example, here TA plus is on, here TA minus is on, etc. So I'm switching on and off these two transistors. The current here should be, as an average value, should be 0. But what about the instantaneous value? Instantaneous value is something that depends on the voltage that you can have here, the voltage across this inductance. Okay, and the voltage across this inductance is the voltage that appearing here, and this voltage is Vd or 0, depending the status of the switch. When TA plus is on, it's Vd. When TA minus is on, it will be 0. And the voltage V, which is constant. So if you look at the current I, in this phase, the current I is something that is, say, like here, like this one. As an average value, average is 0. Okay, my drawing is not perfect. Again, the positive part should be the same as the negative one. But okay, the average is 0. But the instantaneous value of the current is, say, continuously on and off, positive and negative. Basically, this means that since I have this kind of situation, I'm for a situation in which I have to provide no energy, because if the average quantity is null, the average power provided from the switch power pole to the piezo actuator is null. Okay, the product of the voltage and the current is null. I'm dissipating a lot of power, which are the switching power of the two transistors that are switching on and off. So this is a typical nonsense. I'd like to provide an average null power, but in doing this, I have to dissipate large dissipation power, large dynamic switching power due to the switching action of the two transistors, leading to this behavior. So in that specific situation, I have to change my, say, strategy here. For example, the most straightforward strategy that I can apply in order to have the same results is that I have to recognize that if I want an average current which is 0, this can be also obtained by an instantaneous current which is 0. If this current here, instead of having a, say, triangular waveform, having a value, an average value which is null, is itself null, always null, the average value is again null. And what is the best, say, way to get null current in this circuits, in that specific C situation, is to left both transistors to be open. If I left both transistors open, the current flow into the load is null. The average value, of course, is null, so this is good. But at the same time, I have no power dissipated due to the switching action of the transistor. There are no more switching. So, best alternative switching strategy is to left both TA plus and TA minus off. Okay. Of course, what is the drawback of this situation? I left a, say, capacitor left open. Okay, if the capacitor is ideal, this is exactly what I want. If the capacitor is ideal, no current can flow and the voltage remain constant. And this is the ideal situation. Basically, this is not the case for a P zeta T material, because I can see this is a model just for, say, very oversimplified model. Okay, typically what you have to consider is that here you have some, let's say, parallel very large resistor due to, I don't know, the terminals, or basically also some, say, leakage current flow into the materials. Very small, but it is there. Okay, so these are, say, parasite, for example. And this means that when you left open this capacitor, there is this capacitance, let's say, it will be discharged a little bit due to the presence of this parallel parasitic resistance. So this means that from time to time, I have to close the switch in order to provide, say, a burst of energy flowing to the capacitor and refreshing the voltage across it. So basically, I have to left open both switches, but from time to time, I have to refresh the charges in the capacitor that otherwise will be lost due to this kind of behavior. Okay, what does it mean? That I have to consider just one of these pulses from time to time, for example, for closing this switch in order to put this charge into the capacitor. Okay. This is the overview of what I'm going to design. Okay. Have you questions about what I'm saying? Something which is not clear? Of course, my explanation about the P zeta T material are not exhaustive. Okay. Are just, let's say, a little bit simplified, just to retain what I'm going to use in the next explanations, and not to complicate too much the description with some particulars that are not, let's say, more employed. Okay. If you have questions, I can answer the question here, and then we can move on the one of the possible application of this piezoelectric material. Okay. The application I have in mind is the piezoelectric injectors for automotive. So let me go to the, oh, finally we have this slide. Injectors. Basically, in order to, let's say, get the best performance from a thermal engine in a vehicle, for example, in order to reduce the, let's say, to reduce the gases, the unburned gases generated by the operation of the engine, is to increase, to maintain at a very high level the efficiency of the thermal engine, is very important. It's crucial to adjust in real time the quantity of the fuel that are supplied to the thermal engine. Okay, and the quantity that I have to supply to the thermal engine is determined in real time by multiple parameters. For example, the speed, the temperature, maybe the torque of the engine that is required. Okay? So there is a, say, a computer which is in charge for delivering the correct timing and the current quantity of fuel. Let me call this the injection computer. That has exactly the role of the optimization of the quantity of fuel that you have to inject from the, let's say, into the combustion chamber of the engine, let's say. Of course, from this kind of computation performed, let's say, digitally from, let's say, an onboard computer, we need a specific hardware to make possible the injection of the fuel into the combustion chamber. And this kind of injector are based typically on the presence of a needle. Okay, the needle here is, let's say, something which is indicated here. Okay, this is the part that you can see, let's say, here. Okay, so this is the component here. This is the piston you can have in the combustion engine. Okay, and the needle can be raised up or can be down in order to spray the fuel into the combustion chamber. For example, when the needle is rising up, okay, it makes possible for the fuel to be injected into the combustion chamber. When the needle is down, okay, the opening, the little hole that you can have at the point of this injector are closed, and so you cannot have any injection of this of the fuel. Typically, this kind of behavior, so rising up and down this needle, is performed by using solenoid injectors. Okay, there are typically two classes. One is the solenoid injectors. The solenoid are based on the presence of coils. Okay, in these coils you can make current flow. Okay, current flow in these coils, making possible specific, let's say, action, mechanical action into the injectors to, let's say, move up and down this needle. And then you can have piezoelectric injectors. The advantage of having piezoelectric injectors is that you can have very precise, very fast sub-nanometers movement. This helps in order to have, let's say, a very fine-tuning and precise control of the quantity of fuel that you are injecting into the combustion chamber, helping to optimize the behavior and the performance of the thermal engine of the vehicle. Okay? So the very high performance in cars have this kind of piezoelectric injectors because they reduced, for example, the unburned gases, reducing, let's say, the poisoning level in the environment, and then you can get also, let's say, maximum efficiency of the motor, reducing, let's say, the quantity of fuel that is wasted, etc., etc., etc. So, for example, this slide here show exactly the situation, the cross section of this material, in which we have here a stack. This is a stack of PZT, exactly the same, let's say, the construction that I commented on before, which you have very thin slides or PZT materials with multiple mechanical connection, and then you have, let's say, a voltage that is applied to it in order to make, say, elongation, deformation, displacement or not. Okay, in this kind of displacement that can be exploited in order to say, made this needle to be going up and down. Okay, how many times in a four-stroke engine you have to spray these in the fuel into the combustion chamber? This is done 2 times for cycle. Okay, 2 times for, say, complete rotation. Okay, so 2 times. for revolution. The use of a piezoelectric injector makes possible also to, let's say, as I said before, since they are very precise, very fast, sub-nanometer variation of the position, I can also use a strategy of injection of the fuel that makes possible to, let's say, enhance the tuning of the quantity of the fuel which is injected by using multiple, let's say, injection, not just the injection, say, in one single burst, but to divide the overall quantity into a very small injections. Okay, this is the multiple injections strategies for this kind of motors. Okay, so the goal in my, say, design here is to design a driver for this kind of piezoelectric injectors. Okay, and the driver is, as I said before, an half bridge, because I'm modeling my piezo injector as a capacitance. The capacitance here is can be very large, because you have, say, maybe hundreds or even thousands of single stack of piezo materials. That means that you can have several small capacitance in parallel. Okay, in that situation you can have large microfarad capacitance to be driven. This is what happens. So let me just to consider our specification for this exercise. Okay, so let me just to copy this page. Is here. Okay, data are the following. Let me call VP the voltage across the piezo injector, across the piezo actuator. Okay. Versus time, I have that the overall cycle operation is called T cycle, and T cycle is 20 milliseconds. What does it mean? That I have here 20 milliseconds means 50 revolution per second. Okay. How many revolution per minute? I have to multiply it by 60. So you have 3000 RPM. And I have a interval which is called TB. We can call it here T burst, the interval in which I have to inject my fuel into the combustion chamber. So TB is exactly 10 milliseconds. And here I have several pulses. I have 10 pulses here. So the period of each pulse, let me call here, is called Ti. And Ti is exactly 1 millisecond. So the voltage here range from 0 to Vp max. And Vp max is 200 volt. Okay, so what does it means the presence of these pulses? For every pulses, I'm just getting a deformation, a displacement of the piezo material. Okay, this is the voltage across the piezo material. So when the voltage is 0, then you have the rest position. When you apply 200 volt, you can get the displacement you need for injecting your fuel. So you can see here there are multiple injection of the fuels in order to precise control the amount of let's say the amount of fuel that you are injecting. Okay, I have just indication about the period, but I have no indication about what is the width of this pulse, okay, which is the, if you want to say, the duty cycle. I don't know anything, because this is something that I can change in real time in order to make a little bit longer the injection of the fuel, in order to precise controlling all the parameters that I have to control to getting the optimum performance of my engine. Okay, so I know that there are 10 pulses. I don't know which is the width of these pulses, but the number of pulses are quite large enough to be, say, to obtain a very precise control of the of the injected fuel. CP, which is the model for my piezoelectric actuator, is 5 microfarad. It is the PZT material. Then I have some limitation. Remember, the limitation are that I cannot have acceleration very fast. So the maximum voltage that I can, the maximum ratio of the voltage versus the time variation is 2 volt microsecond. And also you have a limitation about the maximum derivative rate of change of the current versus time, which is 1 amp over microsecond. Okay, this is something which is related to the way the piezo material are, say, constructed. Okay, it's something which is related to the necessity to avoid breaking of my material during nominal operation. Okay, so just to finish this computation, I said that my injection occurs 2 times for a complete revolution. So since I have 2 times of this injection for a complete revolution, it means that my motors in my, say, my engine, my thermal engine in this example, is rotating at 6,000 revolution per minute. Okay, this is my example, 6,000 revolution per minute. So let's say we have defined the specification. Okay, just just amplify these pulses, zoom in, because this is the pulse to which we are interested. Okay, we have time, this is VP, this is something like this. The ideal pulse that I drawn in the picture is something like this. Okay, I have 0, I have TI, this is VP max, and this is 200 volt. TI is 1 millisecond. Then I have that the VP over the T is limited here, so the drawing here is not correct. You have no vertical edges, but just you have something which is related to the maximum repetition here. Okay, so starting from this point, tomorrow we can start designing these driver for these piezoelectric actuator, piezoelectric injectors. Okay, have you questions about this topic? Something which is not clear? Whatever. Marco Cannone asks, what about analog controller, digital controller in a unique bidirectional converter? Which technique is used? The PID. I didn't talk about the closed loop, the feedback loop for the controlling, because it depends on the characteristic, it depends on the dynamic of the motors. Okay, and this is a topic which is not, let's say, something that I can not afford here. Okay, of course you have to make the system which is stable, and so you need something in your closed loop that is needed to compensate the loop gain of my closed loop system. Okay, typically this is done with something which can be made by, say, compensator, by, say, some transfer function, which includes some proportional terms, integral terms, integrative terms, or also derivative terms. Exactly in the same way, remember the the lectures that we had for the DC motor control action, which I say schematize in a simple form, the way I have this kind of closed loop, then that is the situation, okay? The PID, for example, is something that you can use, or also simply the PI, okay? Refer to the lecture about the DC motor control, which I overview this material, okay? I not included here in this explanation, but you can find some reference in what I said that situation. For example, that I indicated here the speed control, okay, and the current control, and the way I can design the PI speed control and the PI current control, okay. This is exactly the way I can do that. Emanuele, I get lost in the finding of 600 RPM on the right. Simply because I convert the period into a revolution per minute. Okay, 20 milliseconds are 50 revolution per second, and so 3000 revolution per minute. But remember that I have to inject the pulses 2 times for each cycles. Okay, so it means that I have to say get twice this revolution per minute if I want to get the revolution of my motors. Okay. Other questions, problems, issues? Okay, if you have no questions, I'd like to thank you, all of you, for your attention. See each other tomorrow morning at 10 a.m. See you, bye.